Hey everybody, today we are starting our new unit on trig identities. This is trig expressions that are equivalent to each other, and we're going to be proving that expressions are equivalent. So this is a little different in that we're not solving to get a final answer. We're solving to get an expression that's equivalent. So a little review. First, the reciprocal trig functions. Cotangent is the reciprocal of tangent. So cotangent is 1 over tangent. So then when those are multiplied together, tangent times cotangent, that's the equivalent of tangent x times 1 over tangent x. Well, those tangent x's will divide each other out, leaving us with just 1. So when we multiply reciprocals together, the result is 1. Cosecant is equal to 1 over sine. So cosecant x and sine x are reciprocals. Again, if those are multiplied together, sine x times cosecant x, that result is 1. Secant x is the reciprocal of cosine. So secant x is 1 over cosine x. Then when cosine x and secant x are multiplied together, that result is 1. Okay, and remember those reciprocals work the other direction as well. Tangent of x is equal to 1 over cotangent x. And sine of x is equal to 1 over cosecant x. And cosine x would be equal to 1 over secant x. Those reciprocals work in either direction. There's two other identities that are very useful involving tangent and cotangent. Tangent of x can be expressed as sine of x over cosine of x. If you think about the opposite adjacent hypotenuse relationships, you can figure out where that comes from. Okay, cotangent is the reciprocal of tangent. So cotangent flips and is cosine x over sine x. So the cotangent has cosine on top. Cotangent x is cosine x over sine x. Okay? Now, what we're going to be doing here is proving these identities are true. So if we look at part A, tangent of x equals secant of x over cosecant x. We want to simplify or rearrange we want to rearrange secant x over cosecant x and prove that it does end up equaling tangent x. Okay, so secant x is 1 over cosine x. Cosecant x is 1 over sine x. So we're dividing by a fraction. Remember this, to divide by a fraction, if you have a over b and you're dividing that by m over n, remember, leave the a over b alone, change to a multiply sign, then flip the bottom fraction. So in order to simplify this, we would leave the 1 over cosine alone, multiply that by, flip the bottom, sine x over 1. Then multiplying that together, we just multiply straight across. So that ends up equaling sine x over cosine x. Well, we know from right here that sine x over cosine x is equal to tangent x. So we had tangent x in the original expression. We rearranged what it was equal to, showed it was still another form of tangent x. We're done. That is what we were asked to do. We're not solving for a number. We're not trying to find x. We're trying to show that those are equivalent. Okay? So let's take a look at part B. Similar type problem. We have cotangent x equal to cosecant x over secant x. So we are going to express cosecant x as its reciprocal, 1 over sine x. Same thing with secant x. It's the reciprocal of cosine x, so it's 1 over cosine. Then we will divide. We'll leave that 1 over sine x alone. Multiply by the reciprocal, so cosine x. Multiplying that together, we get cosine x over sine x. Well, we know that cosine x over sine x is equal to cotangent x. So again, we showed that cotangent x in one form does equal another form and still does equal cotangent x. We rearranged or simplified the right-hand side of that equation and showed that it was equivalent to cotangent x. So in number 2, we are looking at equivalences. We're looking for what is equivalent to cotangent x. There could be more than one right answer here. Part A is 1 over cosine x. If you look at those reciprocals, 1 over cosine is equal to secant x. So A is not it. If we look at B, sine x over cosine x, that's an identity for tangent x, not cotangent, so B is out. Okay, if we look at C, secant x over cosecant x, that might look a little familiar because we just did it in part A above. Secant x over cosecant x is tangent of x, not cotangent. So answer D, C is out. Excuse me, C is out. Okay, D, I'm going to simplify down here. We have a cosine x on top over this sign with a 2 and a square right here. That means sine squared x. It's exactly what it seems like. It's sine of x times sine of x. We put the square on the sign so that you're not tempted to square the x. It's not just the x that's squared, it's all of sine x that's squared. So sine x times itself. Then the cosecant x is 1 over sine x. In that denominator, we have a sine x and a 1 over sine x. Those divide each other out. 1 factor of sine x divides out with 1 over sine x. So that leaves us cosine x over sine x. Cosine x over sine x really is cotangent x. So D here is equivalent to cotangent x. Now, it may not be the only one, so let's look at E. E has a sine x in the numerator over cosine squared x. So that's cosine x times cosine x. Then secant x is 1 over cosine x. So we have a factor of cosine x dividing out with 1 over cosine x. Then that gives us sine x over cosine x. Sine over cosine is tangent x. So E is not equivalent. Answer D is the only one here equivalent to cotangent x. All right. We're going to jump down to example 4. And we're going to transform these trig proofs. What we're doing is showing that sine x times cotangent x is equal to cosine x. We're using those trig identities to determine that. So, a couple pieces of advice. These are really helpful, y'all, I promise. A couple pieces of advice. Start simplifying. With the more complex side, left or right. Start simplifying with the more complex side. Okay. Also convert convert all of your trig functions into sine and cosine. If you'll convert all those into sine and cosine, that can help a lot, especially if the entire expression is just multiplied and divided. Sines and cosines help a lot. So here on part A, the more complex side is that left side, sine x cotangent x. So we want to simplify it, and we want to convert it into sines and cosines. So I'm going to leave that sine x alone. Okay, multiply that by cotangent x. Cotangent x has cosine x on the top, then sine x on the bottom. Okay, when we simplify that, sine x over sine x divides out. If you like it better, you can put that first sine x over 1 so you have fractions through the whole thing. Okay, then that does actually equal cosine x. We're done. This is what we were doing, was showing by simplifying with known identities that that left side was equal to the right side. So when we converted cotangent into cosine over sine, that simplified to equal cosine x. That is what we were showing. So on part B, again, we want to start on the more complicated side. It's obviously that left side, that big fraction, and we're converting that into cotangent x. So 1 over sine squared x, remember, is sine x times sine x. Cosecant x is 1 over sine x. Secant x is 1 over cosine x. So I converted everything into sines and cosines. Okay, we have a factor of sine x that divides out with 1 over sine x. So we still have a 1 in the big numerator over, this would be sine x over cosine x. Okay, now we've got a couple choices from here. Sine 1 over any fraction just flips that fraction. So this flips to cosine x over sine x. 1 over a fraction flips the fraction. It's the same as dividing with that fraction, flipping it and multiplying it. Okay, we do know that cosine x over sine x is cotangent x. So we showed by simplifying with identities that those are true. Now, another way to do this, from 1 over, from 1 over sine x over cosine x, same problem, different way. We can convert sine x over cosine x into tangent x. And 1 over tangent x is cotangent x. Again, we proved just with a little bit different way that those are equivalent. And you'll see that there will be more than one way to solve these. So looking at C, it actually does ask us to solve this in 2 different ways. Transforming sine x, secant x, cotangent x into 1. Looks like a lot of stuff to equal 1. So let's figure out what's going on here. I'm going to leave that sine x alone, put it over 1. Secant is 1 over cosine x, and cotangent x is cosine x over sine x. Now, we start simplifying. A sine x divides out with a sine x. Cosine x divides out with a cosine x, leaves us with just 1. Check. Now, this asked for 2 different ways. So another way to do this would be to leave again that sine x alone. Express secant as 1 over cosine x. Then multiply those together. That will be sine x over cosine x. Well, sine x over cosine x is tangent x. So then we'd have a tangent x times the cotangent x. Those are reciprocals. That equals 1. So instead of doing this in parts, we can do this all at once. Okay? All right, give yourself a little break. Pause this video. Give yourself a little break. Look over anything you need to. Really, really, really start to study those 5 identities on the very top of the first page. Those are extremely helpful. You really, really want to know those well. All right, part 2 of today's lesson, a little bit of a review. Cosecant x, cosecant is the reciprocal of sine. So cosecant x is 1 over sine x. Secant x is 1 over cosine x. Then the sine x over cosine x is tangent x. And cosine x over sine x is its reciprocal, cotangent x. Don't forget, when you multiply reciprocals, that result is 1. So sine x times cosine x is 1. Cosine x times secant x is 1. Tangent x times cotangent x is 1. Okay? Now, we have some Pythagorean identities. That's going to be the new piece in today's lesson. These are based on Pythagorean theorem. If we have a triangle in the coordinate plane, one leg sitting on the x-axis, theta in the corner at 0, 0, just like we did with exact values. The lengths are x, y, and r. So x squared plus y squared equals r squared. Okay, this point P, kind of traveled. This point P is x comma y. Okay, so that x coordinate is the length. That y coordinate is its height, and then r is the hypotenuse. So x squared plus y squared equals r squared is just Pythagorean theorem. If we divide by r squared, you see what we get in that second step. Then remember that x over r is the ratio for cosine. So x squared over r squared is cosine squared x. Y over r is the ratio for sine. So y squared over r squared is sine squared theta, and that's equal to 1. So this identity here becomes really, really important. Sine squared x plus cosine squared x is equal to 1. Now, you may need this solved for one function or the other. So if we needed sine squared x is 1 minus cosine squared x. Also, we can solve this for cosine squared x. Cosine squared x is 1 minus sine squared x. Okay, so these other rules come from that basic Pythagorean identity. Now, there are 2 other Pythagorean identities that come from this one. Okay, one of them involves dividing each term by cosine squared. You see the result here. So one of the other Pythagorean identities is tangent squared x plus 1 equal to secant squared x. Then there's a third one. If we divide the original by sine squared x, we get 1 plus cotangent squared x equaling cosecant squared x. If you're looking at these and you're thinking, I'm never going to be able to remember those, I have a solution for you. It's a hexagon, and it's magic. Okay, maybe not technically magic, but it's really, really, really helpful. Okay, so to help ourselves remember this, to help ourselves remember or figure out those Pythagorean identities and to remember some of the others, we draw them on a hexagon. Hexagon has 6 sides, And the further we go into this unit, the neater my hexagons will look, I promise. For now, bear with me. Okay, 6-sided figure, make the top and bottom horizontal. Okay, then we're going to put our trig functions around it. Actually, we're going to put a 1 in the middle. Put a 1 in the middle. We're going to use that in a minute, I swear. So on the hexagon, on the left, start with tangent x. We know that tangent x is equal to, we're going to go around the circle, around the hexagon, sine x over cosine x. That's how we're going to start the hexagon. Now, for the other pieces of the hexagon, we're going to use the reciprocals. Straight across. Tangent x, straight across. Its reciprocal is cotangent x. Sine x goes straight across. Its reciprocal is cosecant x. Cosine x goes straight across. Its reciprocal is secant x. Okay? Now, the beauty of this is it takes one fact to remember how to do this. Tangent x equals sine x over cosine x. Tangent x equals sine x over cosine x. Then you just need to know the reciprocals. Put the reciprocals straight across the hexagon from its original function. Okay? Now, the beauty of this is that the relationships work all the way around this hexagon. Meaning, we already talked about how sine tangent x was equal to sine x over cosine x. We remember, too, that cotangent x is equal to cosine x divided by sine x. That relationship works all the way around the hexagon. Okay? So, for example, sine x is equal to tangent x divided by secant x. Okay? We could also say that cosecant x is equal to secant x divided by tangent x. Okay? It works in either direction. Secant x, we'll start with secant. Secant x is equal to cosecant x divided by cotangent x. And around the circle in any direction, around the hexagon in any direction. Okay? Now, we started this to help you with the Pythagorean identities, the squared ones. Okay? The very first one we talked about was sine squared x plus cosine squared x equaling 1. Let me show you how this works. Sine squared x plus cosine squared x equals the 1. So that pattern makes the number 7. It's a little easier to see if you make that 7 big. Okay, so if we have this 7 in this little piece, okay, that sine squared x plus cosine squared x is equal to the 1. Now, one of the others was tangent squared x plus 1 equal to secant squared x. Tangent squared x plus 1 equals secant squared x. Again, it's along the number 7. So the other place this works is in a third piece of the hexagon. 1 plus cotangent squared x is equal to cosecant squared x. And those are your Pythagorean identities. So as you draw the hexagon with the top and bottom horizontal. Top and bottom are horizontal pieces, not slanted pieces. Okay? Any piece of the hexagon where you can naturally draw the number 7 makes a Pythagorean identity. A plus goes across the top of the 7. Equal sign goes down the side of the 7. Okay? And this is how you can remember those Pythagorean identities. Okay. As I work things in this unit, I have a hexagon labeled right next to me. There is one taped to my computer monitor right now. And it will stay there through this unit. Okay. So those Pythagorean identities again, sine squared x, this is the one that will come up most often. Sine squared x plus cosine squared x is equal to 1. Okay. The other one on the bottom left, tangent squared x plus 1 equal to secant squared x. And then the one on the bottom right, 1 plus cotangent squared x equal to cosecant squared x. Those are your 3 Pythagorean identities. Okay. Be aware you can solve any of these for a different function. So in the second one, tangent squared x plus 1 is secant squared x. That could be solved for tangent squared x. Tangent squared x would equal secant squared x minus 1. Or cotangent squared. If we wanted cotangent squared x by itself, that would be cosecant squared x minus 1. So you can solve these with basic algebra and rearrange them. Be a good idea to practice labeling a hexagon. Will be a good idea to write that down several times. Okay, and I recommend you keep one next to you as you work these problems. I do it. I keep a hexagon next to me when I work these problems. So take a look at number 2. We are looking for what is not equivalent to cosine squared x. Not equivalent. Okay, if we look at these Pythagorean identities, if we look at A, okay, 1 minus sine squared x. If we get cosine squared x by itself, it is 1 minus sine squared x. Watch that order when you subtract. Okay, so A really does equal cosine squared x. It's out. Okay, then on B, cotangent x over secant x, cosecant x. Yeah, I'm going to simplify B up here. Okay, cotangent x is cosine x over sine x. Then in that denominator, secant x is, let me make it look a little different, 1 over cosine x. Cosecant x is 1 over sine x. So to divide with fractions, leave that first one alone. Cosine x over sine x. Then multiply by the reciprocals in the denominator. So that would end up being multiplying by cosine x over 1 and multiplying by sine x over 1. So we have a sine x in the denominator, divide out with a sine x in the numerator, and that's equal to cosine squared x. So B does equal cosine squared x. It's not the answer choice we're looking for. Okay? In answer C, we have a subtraction in that numerator, cosecant x minus sine x, all over cosecant x. We can't divide out the cosecant x's here because of that minus sign. Okay, so we have cosecant x over cosecant x minus sine x over cosecant x. We're splitting that into 2 fractions. Both pieces are divided by cosecant x. Now, any value divided by itself is 1. So cosecant x over cosecant x is 1 minus sine x over cosecant x. Those are reciprocals and we're dividing them. So that would be sine x times sine x being the reciprocal of cosecant. Okay, so that is 1 minus sine squared x, which is cosine squared x. So C is not the answer we're looking for. On part D, we have 1 over secant squared x. Okay, that's 1 over cosine squared x, which is cosine squared x. Secant is the reciprocal of cosine, so 1 over secant squared is cosine squared. So again, D is not equivalent. Okay, that leaves E as the correct answer, meaning it's not equivalent to cosine squared x. Now, it looks pretty similar. Okay, the identity is sine squared x plus cosine squared x equaling 1. So to get cosine squared x by itself, it would be 1, and then we subtract the sine squared x. So sine squared x minus 1 is the opposite positive negative signs from what we need. So answer E is actually equivalent to the negative of cosine squared x, not positive cosine squared x. Very similar. In example 3, we're going to be simplifying trig expressions and proving that they're equivalent. So if we look at 3a, we have that expression on the left, 1 plus cosine A times 1 minus cosine A. To work this out, double distribute. 1 times 1 is 1. 1 times minus cosine A is minus cosine A. Cosine A times 1 is plus cosine A. Then cosine A times minus cosine A, it's a negative. Cosine times cosine is cosine squared A. Then combine your like terms. Yeah, even though they're cosine A's, they're still like terms. So minus cosine A plus cosine A zeroes itself out. And we have 1 minus cosine squared A. Hopefully we're getting a little more used to that identity. That does equal sine squared A. If we look at the original identity, sine squared x plus cosine squared x equal to 1. Okay, if we have 1 minus cosine squared x, it moved that cosine to the other side, leaving us with sine squared A. So we showed through algebra and identities that that was equal to sine squared A. And that is what we needed to do. So looking at part B, we have cosine squared x minus sine squared x, not a plus. And we're transforming that into 1 minus 2 sine squared x. So the left side has a cosine and a sine. The right side only has sines. So I'm going to take this cosine squared x, write it as 1 minus sine squared x. Then there was still a minus sine squared x on that side. And now we're going to combine like terms. Minus sine squared x minus sine squared x is 1 minus 2 sine squared x. And this is what we were asked to prove was equivalent. Because the right-hand side of the original problem only had sines, no cosines, converted that cosine squared x into an expression with sine squared x. Now, looking at part C, we are multiplying this out. Remember, to square something, you are multiplying it by itself. So this is cosine m minus secant m times cosine m minus secant m. And again, we'll double distribute to multiply all that out. Cosine times cosine, cosine squared m. Cosine times minus secant, minus cosine m times secant m. Then minus secant m times cosine m. And then plus secant squared m. All we did there was double distribute. Okay? Now, if you notice right away, cosine and secant are reciprocals. So cosine squared m stays, minus 1, because cosine m times secant m is 1. Then minus another 1. Secant m times cosine m is again 1. Plus secant squared m. Okay? Now, cosine squared m minus 1. Cosine squared m minus 1. We know from the identity sine squared x plus cosine squared x was 1. Cosine x minus 1 would mean we had sine x by itself, sine squared x, but that would equal, 1 minus cosine squared x. We have the opposite. We have a positive cosine squared x and a minus 1. So that's actually a negative sine squared x. Put a negative on the sine squared, put a negative on the 1, change the sign on the cosine squared, and we have a negative 1 plus a cosine squared x equaling that negative sine squared x. Then, on the other trig identity, we have a secant squared m and a minus 1. We have a secant squared m with a minus 1. I really like that to write right there. So, if we look at that hexagon for the secant squared m, I'm going to scroll back up to it. Here's our hexagon. Okay, that secant squared. Okay, we have, it's that second trig identity, that second Pythag identity. We have tangent squared x plus 1 equal to secant squared x. So that tangent squared x by itself would be secant squared x minus 1. If we look at our problem, we have a secant squared x and we have a minus 1. That is a tangent squared x. And I changed somewhere to m. Kind of surprised I waited that long in the problem to change them to x's. Okay. Now, this is one of the more challenging problems, but we do have tangent squared m minus sine squared m. Okay, we have it in a different order, but the positives and negatives match, so it's the same. Okay, so going back through this one, first thing we did was double distribute. Then secant times cosine is 1. So we had a minus 1 for each of the middle terms. And knowing I had to transform them into other trig functions, I didn't add those ones together. Okay, left those minus 1s in the problem. Okay, so looking at D, left the 1s in the problem, then use the Pythagorean identities. If you're converting squared trig functions into different trig functions, look at those Pythagorean identities. Let that hexagon help you. So on part D, we're converting tangent x plus cotangent x into cosecant x times secant x. So we need to convert two expressions added into two expressions multiplied. So we need to be really careful about how we do that. We have tangent x plus cotangent x. I'm going to go to sines and cosines. So tangent x is sine x over cosine x plus cotangent x is cosine x over sine x. Okay? Now, we need to be able to add those together. In order to add those fractions, we need a common denominator. Denominators are cosine x and sine x. Those don't have anything in common. So we'll multiply that first fraction by sine x over sine x. We'll multiply that second fraction by cosine x over cosine x. Now we can add those fractions together. Okay, we have the same denominator, sine x times sine x, sine squared x, plus cosine x times cosine x, cosine squared x, all over that common denominator of sine x times cosine x. And again, because we have that plus sign in the numerator, that ruins us from being able to simplify anything by dividing out, because that numerator is not multiplied, it's added. Okay, then we know that sine squared x plus cosine squared x is 1. So that's 1 over sine x times cosine x. Okay, we can think of that as two separate fractions now because that denominator is multiplied. 1 times sine x over 1 times cosine x. 1 over sine x times 1 over cosine x. Well, 1 over sine x is cosecant x, and 1 over cosine x is secant x, and that is exactly what we wanted to prove. So this is a little bit different from what we've been doing. This is more reasoning and simplifying than it is solving for an answer. Okay. Highly recommend that you know those top 5 identities on the top of the first page, the reciprocals and the tangent and cotangent rules. Also, learn how to draw that hexagon and label it. That will help you with those Pythagorean theorem-based identities there. All right, that's all for notes today.